Well,
They don't need motivation.
they miss that. Yeah. Okay, so we're going to take the unit we just finished and go into chemical bonding. That's what it was all about. Understanding the properties and structure of atoms is really just so we can get into how do they bond to each other. Because that's really what's interesting and important here. Why is the world not just a bunch of loose atoms floating around in empty space? Why did they kind of come together to form the structures, including us, through this process of bonding? How do we understand that? So there are some problem set questions that I'm going to ask you to look at over the weekend. I know it looks like a lot, but these are not like math problems that you have to sit there and spend, and it's mostly conceptual stuff. So let's see how far we get, and then we'll look at how much this makes sense. So we begin. Whoop.
Didn't work.
Oh yeah, I'm on the wrong screen. Whoop. We begin our journey with ionic bonding, but first kind of a brief interlude of bonding in general. What does it even mean to bond? Yes, quite so. Well, the first thing I want you to know is the broad idea that there are three types of primary bonds that atoms can bond through with each other. And there are patterns to these bonds that you can look at just by knowing what kind of elements are involved. Underneath the hood, primarily, of all chemical bonding is that force of attraction. Again, I say electrostatic because that's the force between charged particles. But ultimately, all chemical bonds are based on the attraction of opposite charges. And we know that atoms have those charges because the nuclei have the protons, which are positive, and then they're surrounded by electrons, which are negative. And somehow, the nuclei of different atoms can interact with each other's electrons. And depending on that interaction, we get different types of bonds that imbue materials with different kinds of properties. So when we look at what we call ionic bonding, ultimately, this is very quickly predictable by just recognizing that a metal and a nonmetal, when they're involved, they go through this type of bond. What does that mean? In the case of ionic bonding, electrons are transferred from the metal to the nonmetal. And when that happens, we form positive or cations, negative anions, and those ions can then come together to form a bond. That attraction between the ions holds them together. So what are the key things to know about this? Metal, nonmetal. Metals give electrons to nonmetals. They form ions that attract. But that's not the only kind of bonding we can have. We have our second category, covalent bonding. Probably even more important in many ways than ionic, because it is really the basis of what holds us together. We are a bunch of organic chemicals that are mostly covalently bonded to very complex structures. But in that case, it happens typically between just nonmetals and other nonmetals. When all the elements involved are nonmetals, then we get this type of bonding. And I'm going to put the word sharing in quotes, because sharing is a human trait. And we don't want to use that kind of word when we're talking about physical systems, although it gives us an image to hang on to. But when I say electron sharing, what I mean is multiple nuclei, multiple atoms, can attract the same electrons at the same time. So a nice analogy for that would be two people in love with the same third person. Think about it. You ever been in that situation? You have a boyfriend or a girlfriend, but somebody else likes that person, and you're all kind of in the same friend group, but because of your mutual attraction with that person, that third wheel always hangs out with you, tries to hem their way in. You know what I'm talking about. Come on, you're in high school, for God's sake. Right? But it forms a bond because you're both attracted to the same person at the same time. It kind of holds it all together. Non-metallic bonding, which is our third type, you'll notice clearly kind of we fill out the obvious possible combinations. And that is, this is when metals combine with other metals. But the way that happens is very interesting and kind of a hybrid of these two models. Because here we have electron transfer, here we have electron sharing, here we kind of have both. And so you'll notice I put communal sharing. And again, we're going to get into these mechanisms much more deeply, but I just wanted to lay it out in front at the beginning. What do I mean by communal sharing of mobile electrons amongst a group of metallic atoms? What's that? Mobile?
Yeah.
So it's, if we look at like ionic bonding, you have an atom with electrons around it that kind of stay around it. And then you form the ions, and an electron goes from this atom to that atom, now it stays on this atom. It doesn't move throughout the body of the material. In covalent bonding, the sharing again happens between two specific atoms and the electrons are localized. They're kind of forced to stay in one place. Mobile electrons means these electrons, while they're being shared, are kind of free to move around from atom to atom. They're not stuck. They're called delocalized. The analogy I would picture in my mind is if I took, for example, a jar full of marbles and I poured honey in it, what would happen? Where would the honey go?
Between the marbles.
Yeah, and if you started tilting the jar, wouldn't the marbles start to slip around?
Yeah.
And the honey would still flow between them and keep moving? And it's sticking them and hold it together? It's kind of what I'm describing here, but instead of honey, it's these electrons that are kind of moving between the atoms, and the atoms are attracting those electrons as they're moving around. And that's what makes it different. So any questions about these kind of three shades of bonding before I dive into the ionic form? Have I confused anyone yet?
Yeah.
Okay, well in that case, let me ask you to predict what kind of bonding there would be if I took these two elements together. What kind of bond would you predict between them?
Ionic.
Why? What about something like water? Why? What about my favorite Italian guy living in New York element? Hey, you! Gold.
Oh,
Like my ring. See, my ring is part gold and part platinum. But the outer ring, the yellow one, it's 18 karat gold.
platinum.
Wait, let me, just a recommendation for you folks in the future. When I got this, I had my wife's name and the day we were married scratched in. So I'd never forget my anniversary or my wife. Okay.
Oh.
This is just gold, and the atoms are still held together, right? Metallic. And this would also apply to things like alloys, like brass. Remember the brass we dissolved earlier in the year? It was a mixture of different metals that are bound by this type of bond.
Wait, so if it's just like a metal on its own, then it's metallic?
Yeah. Or even a mixture of metals. And we get into alloys kind of in the follow-up unit to this one. And we'll get more into the properties.
Wait, so what's being shared if it's just one element?
Well, remember,
The metal,
when I look at one element,
same metal.
it's really an array of those atoms. It's not a single atom, right? One element is not made of one atom per se. Like, do you think my gold ring is one atom? But there's lots of zillions of atoms in here, and something's holding them together. And it's these attractions that we call metallic
Wait,
bonds.
is it the same with covalent?
Now that's interesting because covalent bonds can form individual molecules. Like when we write, and we're going to learn this in this unit, we can write a structure like this that shows a specific bonding between atoms. So in the case of water, we can form a single molecule. But there are also structures where covalent bonds can form a crystal, an array. Kind of like, for example, in a diamond. A diamond is just carbon atoms that are continuously bonded to other carbon atoms with covalent bonds. That's what makes it such a tough material.
Oh, so it's just carbon. Oh, okay.
Just bonded, 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 bonded. Yeah. And ionic, again, I'm going to get into that more today, and These form crystals, again, three-dimensional arrays of ions kind of stacking together. All right, so I used to hand this out, but I don't want to make this a crutch. Electronegativity we just finished talking about, and it's really important. We only covered it in the last unit because it really becomes important in this one. Now, we should remember the trend. What do you notice, and what did we say about the trend in electronegativity going left to right? And top to bottom? Good. So, here's the point. Fluorine is the most electronegative element. That means in the game of tug of war between elements, fluorine always wins. Tug of war for what? For valence electrons. Who's the biggest loser? Very close, I mean, at the bottom of that row. Right? Now, look at what I have on the board, and think about what this means. Electronegativity is a property we came up with to describe the relative pulling power for electrons. Now let's see if this actually starts to make sense, because why do metals and nonmetals form ionic bonds, but nonmetals and nonmetals are forced to share rather than take?
I'd say in the form of nonmetals and then the metallic bonding as well. They're very similar electronegativity, so they're fighting more rather than metal and nonmetal. There's a bigger difference.
Yeah, that's a key point here. The whole usefulness of electronegativity is it helps us predict the type of bonds that occur. So if you think about it, the metals all have the weaker pulling power, the nonmetals have the stronger pulling power, and it makes sense when there's a big difference in pulling power, the nonmetal can take the electron fully away. But if we're looking at nonmetals wrestling with each other, they're both pretty similar in strength, and so they're kind of wrestling but sharing. They can't quite take it all the way from each other. And same in the metals, just like you said. So that's very good.
Wait, where are the metals?
Everything,
Oh yeah, I know the transition metal. Oh.
all of that is metals, right? Remember the staircase?
Oh yeah,
Notice we left off the noble gases because they don't play this game, right? They don't tend to bond, and we're going to see again more about that in this chapter. So, just to kind of help you visualize what I just said about electronegativity, you see this scale? You don't need to write it down. You don't really need to know a scale. You don't need to look at the numbers. You just have to know the trend. That's the power of a trend. It lets you make really good predictions without having to memorize formulas and numbers. But here it kind of shows you a scale of bond that I want you to understand. Okay? If two atoms are identical in pulling power, they share electrons equally. There's a special name for that. It's not just covalent, it's nonpolar covalent. And I'll explain that in a minute. On the other hand, if you have two dissimilar atoms, like two nonmetals that are not the same, one pulls harder than the other, and we know this by the trend. In that case, we get a polar covalent bond, and then when the extreme difference happens, when we have a really big difference in electronegativity as we see between nonmetals and metals, that's when it rises to the level of ionic. So if it makes you feel better to have a scale and do numerical calculations to compare, feel free. But I think the trend is enough to really get the gist of this. Now let me go back and describe what is polar and nonpolar. Well, think of any context where you've heard the word polar. What does it mean to polarize something? Whether it's political,
freeze it.
not that kind of pole. I know you're thinking like the pole, but it's connected. The Earth has poles. What are the Earth's poles called?
North Pole.
North?
Complete
South
opposites.
pole.
That's it, opposites, right? And when people say your opinion is polarized on something, doesn't that mean you have opposite opinions?
Yeah.
So here it's not opinions or cold or things like that. What do you see polarizing? What are we representing here and here?
Polar opposites.
Charge.
Charge. Think about it. If we share the electrons equally, right? The positive centers and the negative centers kind of average out in the center of the whole structure. So there's no shift in plus or minus that favors either side. Here, because one atom pulls harder on the electrons, even though it can't completely take them away, you'll notice the electron cloud is shifted more to one side of the molecule than the other. So we get like a negative end or a negative pole, and we get a slightly positive end. And the more this happens, the bigger these partial charges are. By the way, that little symbol is a Greek lowercase delta. That stands for partial. And what that is saying is it's not the same as saying an ion here. Partial charge means the electron is leaning to one side. Here we get the full-fledged charges because there's a strong enough difference in pull to move the electron all the way over and form ions. You see how this is basically like a spectrum of leaning? Equal sharing, unequal sharing, stealing. Nonpolar, polar, and ionic. Are we cool? Have I confused you yet? Huh. Let me try harder. Yes.
I'm confused.
What'd I do?
Oh, yeah.
Huh. Go. I never mind. Just ask. What were you gonna
Do
answer?
you want me to ask?
No, I just said that so you don't move faster.
Yeah, I just
Because you said-
I need to process it.
All right, process. While you're processing, let's predict again. What kind of bond would Na and F make?
So you're not
Metal?
Oh, that's
Yeah.
ion.
And
So,
non-metal.
Yeah.
Carbon bonding to carbon.
That's a
What kind of covalent?
Non-polar.
Non-polar, right? Potassium and iodine. Ionic. Sulfur and oxygen, both nonmetals. As long as they're different nonmetals, it's going to have some polarity to it.
Yeah.
Hydrogen and chlorine.
Ionic.
Close.
That's a.
Hydrogen's the tricky one because even though it's on the left, it's still a nonmetal.
It's
Covalent.
covalent.
Question?
Is it only covalent that has like non-polar, polar, and ionic? Like does non-metal and I mean does metallic and ionic like they don't do it?
Yeah, polar and nonpolar just affects covalent bonds. Ionic is just kind of that final, once we've crossed the line into ionic, we're not talking about polarity anymore because we've formed full ions. Yeah.
How do you know if it's polar or non-polar by just looking at them?
Oh, I'd be looking at the periodic table just to know if it's metals or nonmetals. Once I identify that it's two different nonmetals, they're typically going to pull differently. Because as long as they're not identical, they're going to have at least slightly different pulling powers.
So is that why the non-polar one, they're like the same element? So
Yeah.
it's non-polar.
Now, some would argue that sometimes the polarity is small enough to ignore, and we're going to talk about this when we look at structures later, but carbon and hydrogen is kind of right on the edge of being just slightly different. So this is at least technically slightly polar. But some would say it's so small it's ignorable, let's just call that a nonpolar bond, and that's not quite right. So I'll leave it to you to decide how you want to call it. But for the most part, we're going to see later that the important aspect of this is how it plays out in an actual structure, not just looking at two elements at a time. Okay, yeah.
So like, we can think about it as there's three types of bonding and then covalent can have two like separate types.
Yeah, that's good.
Wait, polar means what? Ionic? I mean covalent?
It's still covalent, but there's separation of charge. Here, let me draw it in a simpler way. So if I put a circle here, and I put one plus and one minus right in the center, it's neutral, right? And it's also not polarized, because no matter where I'm standing, I see the plus and minus equal. If I take that same neutrality but separate the plus and the minus, now it's still neutral, right? Still adds to zero, but if I stand here, it looks more positive, and if I stand here, it looks more negative. That's polarized. Hmm?
I don't know, is it like a battery?
I mean, yeah, it has a plus and a minus there, that's right. Makes sense. Batteries are polarized in that sense, you're right.
So is it, is the only way to be non-polar is if it's the same element, or can you have the same element?
Sometimes different nonmetals have very similar electronegativity, so technically you could say it's a nonpolar bond, but for my purposes, the bigger important thing is to understand the trend and principle, and that is dissimilar atoms pull differently, and until they're metal versus nonmetal, it's not dissimilar enough to make it ion. All right, now, this is something we had to kind of course correct you yesterday a little bit. So let me make sure we knock this out of the park with this concept today. Valence electrons. When it comes to bonding, these are the ones that matter the most. They're the ones on the outside. They're furthest from the nucleus. Therefore, they are most weakly held and the easiest to manipulate and move around. Which ones are they? Always the highest energy level. And this is where some of you were tripping yesterday. If I look at an element like nitrogen, some of you were mixing up sublevel with level. When you look at a configuration, what defines the level? Which part of that information is the level?
The number.
The coefficient.
One on them.
Everything with the highest coefficient is part of the same level. And when it's the highest one, it's the valence shell. Did your question work? No. So this has how many valence electrons?
5.
It's 5 valence electrons, not 3. Shell, not subshell. Clear? Crystal clear?
It's 5 because they're both 2, one has 2, one has 3.
That's exactly right. Yeah.
So for the ionization energies, would it be higher if you're taking, like if you take out all 3 of them from 2p, would it be higher when you take the one extra from 2s?
Yes.
Okay.
If you were ionizing this, there would be a bigger change in energy. That's true.
But is it like more, like, how can you tell the difference between that and then,
Because then going into the core is going to be tremendously more energy to remove.
okay, so like 10 times?
Sometimes or more. Yeah. So just to look at the pattern here and how the periodic table really reveals itself, okay? We're going to learn a new lexicon, and if you understand it once, you got it for the whole periodic table where we need it. Because remember, we said that it's only the S and P sublevels we really care about. The d electrons aren't really going to be a consideration for us as valence because we're not really going to do transition metal chemistry. But look at this dot structure and let's understand what this is coming from. So if I put up our periodic table, I have already told you if we're looking at just valence electrons, we can literally go across and go, these all have 1, these all have 2, these all have 3, 4, 5, 6, 7, helium has 2, and these all have 8. And that comes directly from the configuration, and it applies to everyone in the group. And so once I tell you that we're going to start representing the symbols to be more compact, I came up with, I think, one of the most profound philosophical statements of my life about 2 weeks ago in the middle of the night, and I wrote it down. I'll read it to you now. Symbolism is the earliest expression of human consciousness and self-awareness. Let me make my point. Before our brains developed to a certain level, we were like other animals. We didn't see past, present, or, well, we didn't see past or future, we saw present. We just interacted with our environment like animals. Animals still are like that, right? What makes us different? What's one of the earliest evidence that humans were different?
We can speak English.
Right?
We can speak.
Cave paintings. No other animal was painting pictures of things on walls in ancient, like in art, you know, symbols, things to represent things. And this is what occurred to me. Have you ever heard this thing that like people made all these crazy rules in language so only the elite could really learn it, and it became a way to separate the elite, like people, you know, the sons of kings from the average, you know, farmers? Why is language made so complicated? Think about this. I came to my conclusion that people are sorted into classes, rich and poor, elites, and just, you know, everybody else, based on their ability to interpret symbols. The more you can interpret symbols, the more dense your symbology can become in your mind, the higher you will go. That's true in language, it's true in math, it's true in almost everything you can think about. And so all the stuff we're talking about, and this is why I kind of played in my mind this way, is a lot of what we're doing is just understanding or trying to understand symbols. And when you struggle with that, you suffer. I mean, why do you have trouble in math? You don't understand the symbols. Why do you have trouble in chemistry or physics or whatever? It's the symbols that are messing you up. You can't translate. Whoever controls the symbols,
Controls life.
yes, has the power. They dictate the rules. Think about that. So anyway, if you look at lithium, 1s2, 2s1 is already a condensation of what would have looked like this. 1, 0, 0, 1 half. 1, 0, 0, minus 1 half. 2, 0, 0, 1 half. This is the encoding from quantum theory of each electron. This compresses it. Now we're going to compress it again, because the more dense we can make our symbols, the more information they can carry. So instead of writing all of this and assuming, oh, okay, we got how many protons? We're going to take this and say, we just care about the valence electron, 1 dot. So just to help us symbolize things, we're going to show the valence electrons with dots, not including the dot on the I. And then the symbol of the element represents the core and the nucleus and everything else. As long as we understand that symbol, we can interpret it, we can read it. And if you go across the periodic table this way, you can immediately see that I've done the second row following this pattern. So lithium has 1 valence, beryllium has 2. Notice I'm going to separate them until I come back, and you'll see why. Boron has 3, carbon has 4. Remember when we were doing the orbital diagrams? By the way, this is the orbital diagram, this thing. Some of you misunderstood that on the exam, just as a reminder. And we're trying to actually draw orbits. Remember how we said when there's multiple sublevels with the same energy, I should say orbitals with the same energy, they go 1 by 1 first? I'm doing the same thing in this dot structure. You see how I didn't pair them up right away? Once I hit all 4 positions, then I start doubling up until I fill up. Now, where am I getting 4 positions from?
Yeah.
Which are the valence electrons we're always looking at? S and P, right? How many orbitals are there total? 1, 2, 3, 4. Now, as we get farther into this, we're going to see that these are going to blur together and become a new kind of orbital. Are we almost out of time?
Yeah.
Okay, in that case, there's no homework because I didn't get far enough.
Oh,
We'll continue next time.
Okay, maybe I'll do.
We're getting there. Oh, circles?
Yeah.
That's such an outdated and erroneous model. It's going to actually give you more specific information.
I feel like that helps. You can see the outer shell.
I get that, but the problem is it gives you a false other image. And we're gonna be able to see it other ways. Zach, you had a question? How do I count the valence electrons?
And then I'll tag up.
Oh, I gotta turn off the camera.
So I would focus.
Share this question.